Stiennon. I'm currently doing a postdoc at Berkeley in the computer science department. And I want to talk about agents who are modeling other agents. Very pleased to be here today. Looking forward to the discussion. Feel free to interrupt at any time with clarifying questions. An agent can be a person, or a computer program, or an artificial general intelligence. And I'm interested in agents that are good at modeling other agents. So to talk about the kinds of modeling that I'm interested in, let me introduce the game of chicken. So the chicken is a game played between two players in cars named Alice and Bob. And there's not enough room on the road for them to pass. So each player has two options. They can either go straight or they can turn at the last minute. And let's assume that the players have to make their choices simultaneously. So we can draw the payoff matrix. Each player can either turn to go straight. If a player turns, then they end up not going where they wanted to go, so they get 0 points. And if one player goes straight and the other one gets out of the way, then the player that goes straight gets a point because they got where they were wanting to go. And if both players go straight, then they collide and they get -10 points each. Okay. So what sort of strategies can our players do? So there's the maximum strategy, which is to just always turn. That's the safe thing to do. I call that the 0th order strategy. If Alice knows what Bob is going to do somehow, then Alice has some more strategy available to her. She can do an avoid strategy, which is defined kind of as follows. So if Alice believes that Bob will go straight, then Alice turns. And if Alice believes that Bob will turn, then Alice will go straight. And let's not worry for now about how Alice gets a hold of her beliefs. Maybe Alice has prior experience with Bob. Maybe Bob is a computer program and Alice has read its source code. Maybe Bob is a person and Alice is watching his face. Or maybe a combination of those. But we will assume that Alice's beliefs are accurate. There's lots we can say about inaccurate beliefs, but we'll leave that for other work. So, so if, say, Bob is following the avoid strategy, then Alice has an even better strategy available to her, or a more sophisticated one. Alice can scare Bob into turning. So there's the scare strategy, which is the 2nd order strategy, and it goes like this. If Alice believes that Bob is pursuing the avoid strategy.
Sorry, clarifying question. Why say if Alice believes X if Alice's beliefs are true? Why not just say if Bob equals avoid?
Oh, yeah, you can do that.
What's the difference?
I was just trying to conceptually separate beliefs from actual things that happen, because I might want to make those different later on in the talk. So, but yeah, Alice might have some uncertainty about what Bob will do, in which case Bob will definitely do one thing, but Alice will be not sure what Bob will do. Yeah. So, but in this case, Alice has a maximally specific belief, so they're the same thing. Yeah. Anyways, if Alice is absolutely sure that Bob is playing avoid, then a thing Alice can do is to go straight. And if Alice goes straight, that will cause Bob to have an accurate belief that Alice goes straight, which means that Bob will turn to avoid Alice, and then Alice gets the straight and Bob turns. So note that if you expand this invocation of the void with the definition of the avoid strategy, we start getting nested counterfactuals. So if Alice believes that, if Bob believes that, Alice goes straight, etc. So these counterfactuals are getting kind of complicated, and the goal of this talk will be to construct a space of agents that kind of tame the counterfactuals. This is all work in progress, not published yet. So maybe still some details to work out. So let's take a first crack at defining a space of agents. So I'll let A0 be the set of actions available to Alice, which in this case is turn it straight. And those are also coincidentally the actions available to Bob. And looking at this first order strategy here, let's conditionally define A1, the space of first order strategies available to Alice, to be the set of functions from B naught to A naught. So in this case, Alice knows what Bob is going to do, and then what Alice does is a function of that. And symmetrically, B1 will be functions from A naught to B naught. And I'm writing question marks here because I'm going to revise these definitions because they'll turn out to be not accurate.
You mean A0, or A naught?
Yeah, sorry. That's A0. Now for A2. In this strategy, Alice has access to what Bob is doing as a function of Bob's zeroth order beliefs. So it looks like Alice has a belief about a first order belief about what Bob is doing, conditional on his zeroth order beliefs. And we might as well give Alice also a zeroth order belief about what Bob is going to do. So so Alice then is a function from B1 and B0 to A0. And by currying, this is a function from B1 to function from B0 to A0. And that's just a function from B1 to A1. So symmetrically, we'll define B2 to be function from A1 to B1. So this series of type definitions is reminiscent, or basically the same maybe as metagame theory, which was introduced by Nigel Howard in the 70s. But there's a drawback of the type definitions I've given, which you see when you imagine that Alice is playing the avoid strategy, but Bob is playing the identity. So what happens here? Well, so if Alice goes straight, then Bob knows that Alice goes straight, and Bob, being the identity, goes straight himself, and then Alice knows that Bob goes straight, so Alice decides to turn, and that's a contradiction. So if Alice turns, then Bob knows that Alice turns, so Bob will also turn because he's the identity, and then Alice will know that Bob turns, and so Alice will go straight, and that's also contradiction. So there's no consistent outcome when the avoid strategy plays against the identity strategy.
I imagine there could also be more than one outcome sometimes.
Yeah, and I'll get to that. And I think that's not as bad as there being no outcome. Yeah. So, so there's an easy fix to the non-existence of outcomes, which is to add probabilities. So let's allow Alice to have uncertainty about what Bob's going to do, quantified by probabilities. So the input to Alice will now be a distribution over what Bob does. And let's additionally allow Alice to randomize her action. So her action is distribution over actions. And similarly, B1 will be a continuous function from distributions over A naught to distributions over B naught. And then Brouwer's fixed point theorem guarantees that there will be an outcome of fixed point. So Brouwer's fixed point theorem tells us that for every agent A1, A1, and agent B1, B1, there exists a distribution P naught in delta A naught and Q naught in delta B naught, such that P naught is the output of agent A1, and Q naught is the output of agent B1. And then we can interpret this fixed point as the thing that happens, the outcome, when these two agents play the game against each other. And this works for agents of any order. If we follow this pattern and let a sub n plus 1 be functions from delta bn to delta an, and vice versa for bn, and that lets you get an outcome for any two agents of the same order, no matter what order it is. It kind of looks like this. So if we have a second order agent A sub 2 and a second order agent B sub 2, then we can get distribution over agents A1, call that P1, and that's the output of A2, and it's also the input to B2, and the output of B2 is Q1, so distribution over B1, that's the input to A2. So that's the Brouwer fixed point step. And then we can sample an agent from P1, and that'll be called A1. And sample an agent B1 from Q1, that'll be B1. And then we can do the same thing one level down. So we get a distribution over A naught called P naught. That's the output of A1, and it's also the input to B1. And the output of B1 is Q naught. That's the distribution over B naught. And it's the input to A1. And then we sample from P naught, and we get A naught. And that's our actual action. And that's the outcome. Okay, so the sequence of events is kind of two agents somehow get accurate beliefs about each other, and then the output kind of mixed strategies. Sample from those, and we get lower order agents, which are kind of like the computations that the higher order agents defer to after they've consumed a high order belief. And then the deferred agents get to consume lower order beliefs, and then they keep doing that until we get to zeroth order agents which are actions. So that's the basic procedure for figuring out what happens. Okay, so what's the next problem? Yeah, so you might ask what happens with infinite order agents. And in fact, you can define infinite order agents and spaces A sub n for every ordinal n. But that's actually, I think, too many spaces of agents because it doesn't allow an agent to recognize itself. So you might imagine an infinite order agent called twin. And twin is defined by the English sentence, if Alice is twin, then if Alice believes that Bob is also twin, then Alice can reason that whatever Alice does in the game of chicken, Bob will also do. And so Alice is actually choosing from the set of symmetric strategy profiles, and she can select the optimal one, which in this case, by the payoff matrix I just erased, will actually be 1/20th of the time she goes straight, and then 19/20ths of the time she turns. Just a little bit of going straight independently of her opponent maximizes the welfare for everyone, assuming that they're doing the same thing. But if we try to turn this English sentence into a type definition, we get something like A infinity would be functions from distributions over B infinity to mixtures of actions. And then symmetrically, B infinity would be functions from distributions over A infinity to something. And this is a recursive type definition, which we can solve using domain theory, as introduced by Dana Scott. And the way that would work is we would be able to define infinity as the inverse limit of some system of retractions from higher order agents to lower order agents. And I'll get a bit more into the technical constructions later. But there's an obstacle here, which is that A naught is a discrete space and A1 is connected. And so there's no retraction from A1 to A naught. And the only way I've found to make this construction work is to replace probabilities with imprecise probabilities. So I'm going to take a detour and talk about imprecise probabilities next.
Question.
Yes?
Where did this 20 come from? I think I missed it.
Oh yeah, so the matrix
Oh, you're right.
had a negative 10.
Oh, okay,
negative
right.
10. Yeah,
So that
and
was
it
right.
turns out you maximize the utility.
Can you sample from imprecise probabilities?
No, but you can kind of like combine an adversarial choice with a sampling step. And that's kind of like the analog. And then you get like worst case expectation.
Okay.
Okay. I don't know all the people who invented imprecise probabilities, but I think the usual textbook is by James Wally. In order to motivate it, let's go back to the first order agents we were talking about before. So A1 was provisionally maps from delta B naught to delta A naught. A naught and B naught are 2-point spaces, so delta A naught and delta B naught are for newly variables, which are parameterized by a single probability. So A1 is a function from the unit interval to the unit interval, so we can graph it. So horizontal axis is delta B naught, vertical axis is delta A naught. The horizontal axis ranges from 100% turn to 100% straight, same with the vertical axis. Before we were talking about the avoid strategy, where you try to do the opposite of what your opponent does. When you try to generalize that to mixed strategies and probabilities, you have a sort of like, you want to play the thing that maximizes expected utility. So if Bob always turns, Alice wants to go straight. And if Bob always goes straight, Alice wants to turn. And in fact, Alice will want to turn unless Bob almost never goes straight. And then the threshold occurs at 1/11, it turns out, for this payoff matrix. So below that threshold, Alice wants to go straight, and above it, Alice wants to turn and avoid. And the way I've drawn it, it's not exactly a function. If we wanted to make it a function, we could make it a sort of steep sigmoid. But that would be kind of lame because we'd be giving up some payoff when Bob is close to the decision threshold. So an alternative approach is to say that this is a set value function, and that at the threshold, the output is a convex set representing all the different mixtures Alice could pursue between which she is indifferent. So this suggests we might want to replace probabilities with convex sets of probabilities, also known as creedal sets. So a creedal set P on X is a non-empty, convex, closed subset of X. And I want to introduce an equivalent model of imprecise probabilities. So note that if mu is a probability distribution on X, then the expectation functional takes functions, like I call them value functions, to numbers, and that's a linear function. Yes?
Yeah, I think you mean distributions on X.
Yeah, what is X? Like
Oh,
what structure is X?
Thanks. Oh, yeah, thank you.
Okay, thanks.
Yeah. Yep. Okay. A creedal set is a set of distribution on X. Yeah. Right. And then, so if P is a creedal set, then we can kind of generalize the expectation functional and define expectation with respect to P. And this will take value functions on X to R. And yeah, this goes back to the answer I gave to David. So it'll take the function phi to the minimum over all distributions mu in P of expectation with respect to mu of phi. And this will no longer be linear functional, but it'll be superlinear. So that motivates
What is superlinear?
yeah, it means that expectation of P plus Q of no, expectation with respect to P of phi plus psi is greater than the expectation of phi plus the expectation of psi.
What's the motivation for the min? Is just some kind of pessimism? The min, yeah.
Yeah. So you could do it the other way. You could use primum. And this one is kind of modeling adversarial choice or demonic choice. If you had a supremum here, then that would be modeling like beneficial choice. So angelic choice, yeah. So one way to think about a probability distribution is that there's some process that will like impartially give you a sample. And then a creedal set is kind of modeling a process where someone who doesn't want you to win makes a choice, and then after that some impartial process makes a stochastic choice. So the person who doesn't want you to win is choosing the distribution that's worst for you.
You're not also saying that superlinear functions of that form give us creedal sets?
I'm going to add a couple more conditions.
Okay.
Yeah. So, right. So the generalization of that is that a lower prevision P on X is a functional P from value functions on X, non-negative ones, to non-negative numbers, such that the following conditions are satisfied. P of A phi equals A times P of phi for all real numbers A, and P of phi plus psi is greater than P of phi plus P of psi, has superlinearity, and also P of A plus phi is equal to A plus P of phi for all real numbers A, and that's a kind of a normalization condition. Okay, and now I claim that these two definitions are equivalent. Yeah. Oh, so people always ask about why we're doing like adversarial choice, and the best answer I can give is that way you can get lower bound guarantees at the end of everything.
Is there a reason we use non-negative numbers rather than all real numbers if it's a simple reason?
Yes. That way there's a least prevision. Right? Wait a minute, no, that's not true. Well, okay, yeah. I think it's for compactness reasons, actually. Yeah. Well, maybe you don't need that if you have this here. Yeah, maybe, I'm not sure, maybe you don't need it. if
Is it
you
just
have
that the negative would turn the min into a max? Is that?
I don't know.
Yeah, I mean the min is sort of corresponding to the superlinearity, so the
Mhm.
superlinearity makes sense whether they're
Yeah. Okay.
Wait,
Right. Yeah, I don't know.
is that also for all A and R or for all A and?
You can probably restrict this to non-negative A, and I
Well, if you
think.
picked a large enough negative A, wouldn't you run into
Oh.
a domain,
Yeah.
codomain
Yeah.
problem?
So it has to be large enough that this
Mhm.
is a non-negative function.
Okay.
Yeah,
Um,
but I'm not sure. If you just restricted this to non-negative A, you might get it might be equivalent.
yeah, it's equivalent because
Yeah.
you can just move the A to the other side.
Mhm.
Oh, okay. Yeah.
So,
Okay.
you said why, I think superlinear, and you said because we want lower bound guarantee, sorry, what, I've forgotten the exact words, but why do we want these lower bound guarantees?
Oh yeah. Well, so at the end, I want to say that like these two agents get at least this payoff in this game, and that's like a good thing you can say about each agent individually. And like I also like to say like this agent Alice gets like at least this payoff no matter who Bob is, and that's also kind of a guarantee I like to give. Yeah. Yeah, I guess that's the kind of shape of results I'm looking for. But yeah, maybe it's just as interesting to get upper bounds. I just don't feel that way. But I could be wrong about that. Okay.
Maybe you could also say that imprecise probability theory is subsumed or is a subset in some sense of infrabationism.
Oh yeah, that's true. So, Alex Pell and Vanessa Kosoy have also been using imprecise probabilities in their informationism program, and yeah, talking with them has been like an inspiration for the stuff I've been working on. But I'm not an expert on that stuff.
Yeah, you loosen these other restrictions. That's what happens. Not just the superlinearity, but also the A and the homogeneity and the other things.
So it's no longer homogeneous.
Yeah.
Oh, okay. Oh. Okay, I want to make a couple points about domains. So real sets are ordered as they have a posted relation. P is below Q if P is a subset of Q. So above means more specific. And lower provisions also have a poset order. So P is below Q if for all phi, P of phi is greater than Q of phi. And these make Creedle sets and the space of provisions into domains, and then we'll want to iterate. We'll want like to take provisions of provisions. So if we want X to possibly be a domain, and if we do that, then we want to add a couple conditions, a couple of continuity conditions to these definitions. So we'll want to say that a creedal set is an upward subset of the Jones-Plotkin power domain, and we want to say that a provision is Scott continuous.
Maybe you can use a different color.
Okay.
X is a set here, X is a set.
Yeah. X is so X is a set, but we can make a better definition if we assume that X is a domain, like a direct to complete partially ordered set. In which case, delta X, if X is also a continuous domain, then delta X also has the structure of a domain, in which case P is still a subset, but we need to impose this condition on the kind of subset P is.
Wait, what is that condition?
The upward, it means that if A is in P and A is below B, then B is also in P.
Okay, so it's like upward close.
Upward close, yeah. Mm-hmm.
Do you take the same sort of intuition about domains here, which they're about like computation and all partial computations in the order?
Yeah.
Okay, so that's what the output is still taken as like, yeah, in that sense.
Yeah, yeah. So I wish I hadn't erased this picture of the graph, but this graph is like the graph kind of the computation where Alice is deciding whether its input is above 11th or below 11th.
Mm-hmm.
And if the input is exactly 11th, then it takes kind of forever to decide whether it's greater or less than. And so it kind of never outputs something. Never outputting something is like outputting like every possible output. Yeah, so that's like another motivation for going to precise probabilities.
Maybe you could say a very short thing about what domains are, or what.
Yeah. So, right. So a partially ordered set is a set together with a partial order, which is a relation, which is transitive and reflexive, and a partial order can be said to be a direct complete partial order if it has enough suprema in it. And the supremum is a least upper bound. And then say a directly complete partially ordered set is a continuous domain if it satisfies another condition. But I think
That gets in the weeds. It's more
that gets into the weeds, yeah. And then and that we call domain. So I kind of don't want to get into all the definitions of what a domain is.
Yeah.
And I think if you just think of them as sets or topological spaces, then everything should be comprehensible. So if a set has a directly complete partial order, you can put a topology on it called the Scott topology, which is not Hausdorff. And then Scott continuous map means continuous with respect to the Scott topology. Cool. Okay. Yes.
Maybe want to say though that the partial order is supposed to represent partial computation, so it was already mentioned. So you're doing some computation with sort of the information that you have at a certain time stage.
Yeah, I think it corresponds to anytime algorithm in computer science. So you have a program and you're feeding input into it, and the longer the program waits, the more information it gets. And that kind of corresponds to its input going up in the partial order. And then it gets to output provisional answers and then make those answers more specific over time by outputting more information, and then its output goes up over time as well. And then If the output gets more specific as the input gets more specific, then the computation is monotonic. Yeah, in the order.
That's also the Scott continuous condition.
Yeah, and then Scott continuity entails monotonicity, and then it's like, yeah, and then it's like one more condition on top of that.
Okay,
Yeah,
sure,
basically
yeah.
preserves a suprema of direct complete set. So basically, you can compute if like you have an infinite sequence of input data approaching the limit, then the computation will approach the computation commutes with that limit operation. Yeah. Okay. I said something about these two notions being equivalent, so I should say what that equivalence is. First, let's let nabla x equal the space of provisions on x. So claim Creedal sets on x isomorphic to provisions on x. And the way that goes is if you have a Creedal set P, then
Write down min.
yeah, so E sub P, which is yeah, min U and P of f station U. And going the other way, if little p is a provision, then we get a Creedal set, and that'll just be the set of all distributions mu, such that the expectation functional is greater than or equal to p. Actually,
Maybe you want to use.
a square one. Yeah, so it's yeah, greater on all inputs. Okay, so let's see, how am I doing on time? Okay. Okay, let me list some properties. Of the space of provisions. So first, it's a functor. So if f is a continuous function from x to y, then nabla f is a continuous function from nabla x to nabla y. It takes provision p and sends it to the provision that takes the value function phi and sends that to p of phi of f.
So here x and y are domains and f is
Yeah, so x and y domains, I'm assuming that f is Scott continuous,
Okay.
and then nabla f will be also Scott continuous between these domains.
And nabla x also has a domain structure you mentioned.
Yeah, it's the one determined by the poset structure is something's above something else if I'm sorry, I got this backwards. P is below Q if and only if P of phi is less than Q of phi. Sorry about that. Yeah, so it means less than point lines.
So the statement here is that nabla is a functor from the end of functor domain, the category domains.
Yeah.
Okay.
Yep. Let's see, we also have a Cartesian product of provisions. So if P and Q are provisions, then we get a provision on the Cartesian product that sends a value function to P evaluated on the function that sends x, to Q evaluated on the function that sends y, to phi of xy. And if you want some homework, you can try to construct these using Creedal sets instead of provisions. Sometimes it'll be easier, sometimes it'll be harder. Not only is nabla a functor, but it's also a monad. So there's a multiplication from previsions on provisions to just provisions.
Is that symmetric?
Yeah.
You were saying?
I don't think it's symmetric.
Symmetric.
I think at least the infra one is not symmetric, and I think it already is not symmetric for the imprecise one. Exactly for the reason that in normal probability theory, independence can be described in two ways. Namely, it's a product of probability distributions one on x and one on y, or the conditional probability x given y is equal to x. In the imprecise world, that is going to split, and you're going to have a weaker notion, which is this asymmetry, irrelevance, which is an asymmetric notion, and that's going to correspond to the non-commutative view of this one.
Cool, thanks. So if you have a provision on provisions and a value function on x, then what you can do is you can evaluate the meta provision on the function that takes the ordinary provision little p to p of v. Yeah. And unlike the Geary monad, this multiplication is a retraction that has left adjoint. And I'm going to call that new. From previsions to provisions on provisions. And there's no best way to describe this. You could say it sends p to the infimum over all meta provisions capital P that multiply down to p. So that multiplication of capital P is lowercase p. Or if you like, you can think of meta provisions on x as Creedal sets on previsions, in which case this could be, could say it goes to the set of all meta distributions capital N, distributions on provisions, such that for all phi, the expectation for a provision, little q sample from n of phi is greater than or equal to p of phi. And yeah. But I guess I like this one better. And it works because Creedal sets are sets, so you can kind of throw in kind of everything. So, so new is left adjoint to mu, I believe. One final thing, there's a least element bottom in provisions, and it's just the thing that takes the minimum of a function. And there's also a least Creedal set, it's the whole set of distributions.
Is there anything in terms of how it interacts with the exponential? You were saying something like domains are Cartesian closed category, and this forms a Cartesian monad so far with items. We're not quick enough to actually write that statement.
So let's see, the exponential object. So that'd be like, so yeah, so like this kind of thing, and something like, oh, you mean like a tensorial cotensorial string? Yeah, like maybe something like if you have this, is there a map to this, that sort of thing?
Seems like
I haven't thought about this lately, but I wouldn't be surprised if there was some nice object like this.
Okay. Cool.
Yeah.
I mean, if you have uncertainty in the codomain, then you can build that. It seems likely.
Mm. Yeah, I mean, yeah, totally. Yeah. And maybe the other way too. Yeah, I don't know. Cool. Okay, we're now ready to actually define the space of all agents. So let's do that. Okay. So before I've been distinguishing between defines A and B, but like Alice agents and Bob agents, but I'm gonna identify those for brevity. So let's just have A naught be some finite set of actions. And then recursively define A sub n plus 1 to be continuous functions from provisions on A sub n to provisions on A sub n. And then I'm going to define some raising and lowering operators that kind of relate the various spaces A sub n with each other. So if we have provisions on A naught,
So they have the same kind of action space at the very bottom.
Yeah.
That's what they're saying. Okay,
yeah. But if you want different action spaces, you can
It's also
totally
possible.
Yeah, and it should be pretty clear how to do that.
Right, okay.
Yeah. So we can embed provisions into this function space as constant functions. And this function space is just A1. So there's an embedding like that. And that also means that we can first do new, the adjoint to multiplication, and then follow it up with the constant embedding. And we get nabla A1. So we'll call this I0 our first raising operator. And going the other way, if we have A1, a function in A1, we can evaluate it on the bottom provision, and we get provision over A0. So if we have provision over A1, we can evaluate on the bottom, get double provision on A0, and follow it up with the monad multiplication, and to get nabla A0. And this will be J0, our first lowering operation. Now, the const and the eval bottom maps are adjoints, and therefore I0 and J0 are adjoint. And in fact, we can say it more as an embedding retraction pair, meaning that if you first do I and then do J, that's the identity. And if you do the other way, J than I, that's less than the identity, less specific than the identity. Okay. Yeah.
So I guess like, I don't know, this sort of feels like the types just work out. We have like enough, is there more going on, or is it just like, no, the types
Yeah.
work out?
So here, basically all that's going on is that if you have some kind of like distribution over actions, you can instead have some distribution over constant agents that output a constant distribution over actions.
Yeah.
And the new means that if you start with like a 50-50 distribution, you can end up with like a distribution over agents, some of which are more lopsided than others, but on average they even out to 50-50. Yeah. And going the other way. Yeah, and going the other way, if you have like a distribution over agents, for each agent you can kind of like take the range of the agent. Like if there's an first order agent, there are some circumstances in which it will like go straight 90% of the time, in some situations in which it will go straight 10% of the time. And if that represents the whole range of things it can do, then its range is kind of that range of probabilities between 10% and 90%. That's kind of like what this is doing. And now we can recursively define higher order raising and lowering operations. Like so. So I sub n plus 1 is going to go from A sub n plus 1 to A sub n plus 2, and it's going to take an agent little a sub n plus 1 to the composition I sub n of A sub n plus 1 of J sub n, and the lowering operation J sub n plus 1 is going to take A sub n plus 2 to A sub n plus 1, and I'll take little a sub n plus 2 to the composition Jn of an plus 2 of in. And we can also extend these two previsions just by applying the prevision functor. It's 1 and jn plus 1. Now let an plus 2. Now let an plus 1. Now let jn plus 1. So briefly, what it's saying is that if you have an agent and you want like a lower order approximation to that agent, you can just apply the lowering operation to all of the agent's outputs. And if you have a lower order agent and you want a higher order version or cast of that agent, you can just apply the lowering operation to all the agent's inputs. And then recursively we get the whole thing. Then, applying the machinery of domain theory, we can define A infinity to be the inverse limit of the system of retractions starting at A1. And that comes with an embedding retraction pair, I and J, for every n, and an isomorphism between A infinity and maps from provisions over A infinity to provisions over A infinity. Okay, now one kind of weird thing here is that the input to an agent is a belief about agents of the same type, which is good, but the output is also an infinite order agent. So we don't have a story about agents eventually outputting actions in finite time. But I think that's okay, because we can extend the payoff function to pairs of agents, and that gives us basically all that we want. So to spell that out, if U is our payoff function from pairs of actions to reals, and here I'm going back to distinguishing between Alice-shaped agents and Bob-shaped agents. So if we have an Alice action and a Bob action, then how much time do we have? Oh, and over time for into the question time. So cut this short. Okay. What if I give one short example and then we have questions? Does that sound? Yes? Okay. Sorry for going over time. Okay.
We started a little late.
So I'll skip over defining payoffs. Okay, we'll talk about the stoplight. So chicken is a bad game because the only way for no crashes to happen is for one person to just turn and get 0 points all the time. But you can get a more symmetric outcome if there's a stoplight that tells like one person to go half the time, the other person goes the other half the time. And usually you augment the game with some external signal and get a correlated equilibrium, but you can instead just use recursive modeling. So I'll show how that works. So here are some agents. So A0 contains the agent that always goes straight, the agent that always turns. A1 contains the agent called avoid, and I'll write down what it looks like with previsions. So if P is its belief about its opponent, then it goes straight if the expected payoff from going straight is greater than the expected payoff from turning. Or we're using P as a generalized expectation. And turns if the opposite holds, and otherwise up is bottom. So that's the best response first order agent. A1 also contains I0 of S, just the agent that just always goes straight no matter what its opponent does, and I0T. And then A2 contains an agent called follow, which just always outputs the avoid agent. So it just always chooses to do avoid. And the agent called lead, which always outputs a mixture between I0 straight and I0 turn. Okay, and then we can see what happens by drawing out the waterfall diagram. So let's say that Alice is playing lead, Bob is playing follow, then so the beliefs look like this. So lead will output this mixture between straight and turn, and then follow sees that but it ignores it and outputs a void. And then lead sees that but it ignores it. And then we sample from straight and turn. And sometimes we'll get straight, sometimes we'll get turns, so we'll draw them different colors. And parentheses. And then oh, this is I naught. Right, and then the void will oh yeah, so this is really like the singleton point mass on the void. So when you sample from it, you just get void. Okay. And then this will always output straight or turn as previsions on A0. And then the void will see that and output the opposite, turn, or straight in the other case. And then it will sample from that and get straight or turn. And then this will just be turn or straight. Last time there. So either Alice will go straight and Bob will turn, or vice versa, and they'll never collide. Okay. So that's an example of implementing the stoplight. Okay, I think I should break for general questions now.
Questions?
Yeah, that's really great. I didn't quite, it seems like you're driven by quite a clear problem statement, which is roughly of the form to something unsatisfactory about the analysis of chicken. Can you be more precise about what the motivating statement really is?
Yeah. So really I didn't really use it as a clear problem statement because I don't have one.
Oh, okay.
But like basically my ultimate dream is to come up with like a normative theory of what kind of agent you should delegate to if you have to delegate to an agent that's gonna then play games with other agents. And yeah, just formulating what that problem is requires coming up with a type of what an agent is and what happens when agents compete with each other. So that's my ultimate goal. And then the more proximate goal was coming up with a satisfactory space of agents that can reason counterfactually about what other agents would do.
It's almost a question, but it's more of an editorial.
Okay.
So I'm interested in something someone said to me last week was that the ethics or the politics of a closed system is optimization, whereas the politics of an open system is, you know, cooperation and co-creation. The point being that by closed we mean in this case like a set of actions that, you know, are fixed for all time and there's no possibility of creation of new actions. And it seems to me this analysis goes down that path of, you know, assuming that the world we're trying to model has is completely well defined and closed in that way, and then, you know, requires this sort of analysis of higher order beliefs and stuff. Do you have any comments about that, and like whether that's an assumption you're holding about?
I'm trying to.
I don't know whether that makes sense even.
I can maybe guess at like why an open system would involve cooperation, but I'm not seeing why a closed system would necessarily be about optimization.
In that because everything's completely different. Well, I'm just interpreting the statement. I'm still thinking it through. But in a case where all your options are already predetermined by your formalism, then there's nothing else to do than pick the best option. And so in that case, it's a framework of optimization.
Okay, so here's something I can say. I don't know if it's the same thing at all, but like there's kind of two kinds of knowledge that these agents can have.
Right.
So this agent knows everything about this agent because it's observing it, but also this agent could have some assumptions about what this agent is like. That feels kind of more open and this feels more closed.
Right.
And yeah.
Okay.
I don't know if that.
So that's in some sense what you're saying is that modeling beliefs has a generative capacity there, which creates space for different actions or something like that, for more interesting analyses. I don't know.
Maybe.
I mean, you can have these self-justifying, self-generating beliefs. Sorry, I forgot the word. Self-justifying prophecies or something. Self-fulfilling prophecies. Yeah. And there's some work I think by Garibrandt where you can sort of mathematize that. Where what assumption you make is gonna. I mean, obviously we have some idea about that in the real world, but there's also sort of mathematical framework where what assumptions you're gonna make are kind of self-propagate to.
Right.
Yeah.
Well, I guess sorry.
Okay.
What's interesting to me is that the space happens, you know, in the end of the day, if you take the analysis of chicken, still you can only turn or go straight. And that seems a fundamental assumption of the analysis, right?
Yeah.
And that can never be changed.
Yeah, I'm confused about how this degrades into like bounded thinking or something. So I guess one obvious thing is to just limit to some A and think only up to some steps. But then you also mentioned the lattice on the creedal sets and it becoming more and more crisp or something. Is that also a way to degrade it?
Oh
somehow?
yeah. Yeah, so I think you could discretize the probabilities and then the spaces would become finite. And yeah, and that's like would be like another dimension of specificity.
Those seems like three. There's discretizing, there's moving up the higher order level, and there's the precision on the creedal sets. And there's a fourth thing, which is the domain ordering.
Yeah, I think some of those overlap.
The domain ordering is not relevant, right? On the provisions? That's just how much the expected value. Like the ordering on the provisions is not relevant to boundedness, is it?
It is relevant to specificity, yeah. Even though it was defined with the greater than or equal to symbol, it's actually about specificity.
Oh.
Yeah, because roughly, if you have if X is this very simple partially ordered set, 0, 1 bottom, then you can have a distribution which is like a point mass on bottom, and you can have a distribution which is a point mass on 1, and then this will be above that in the post-set ordering because it's more specific. But the way that's related to previsions involves like monotonic value functions that are increasing as you get more specific.
Is that an assumption or?
Yeah, it follows from the definition that I wrote down. If you like interpret things as being about what's that? So yeah, I wouldn't
Oh,
go
is
there.
this because of the non-negativity of the value function or something?
No, it's about the fact that the interval from 0 to infinity has a standard poset ordering. So if we assume that this is continuous and monotonic, then as you get more specific in the domain X, then the value function gets higher. Yeah.
It sounds a bit like the weird monotonicity condition in information physicalism. Maybe. Well, anyway, whatever. That's a bit of a weird remark, but sorry.
Well, why don't we thank the speaker again and we can have more questions
Yes.
later.